اوكي، بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Topic number 5. Okay, so we're done with topic number 4, which is on the stability analysis, the control using Lyapunov, looking at rigid body control, rotation on SO3, trying to reformulate the proportional derivative control on the point mass so that it looks like an energy balancing control where we have a proportional term that comes from the gradient of some potential function. This potential function shapes the total energy of the system such that we have the minimum at our desired point. We also have the derivative term. We interpreted it as something that injects damping into the system so that it will make sure that we stabilize at this point and we have some asymptotic stability results. We're going to be looking today at fixed base manipulators. So we're going to be looking at the control of these type of systems. We've finished the modeling, so you should be now good at the modeling of the fixed base manipulators. We're going to be doing two parts. One which is on the motion control and the other one which is on the force or impedance control. Okay, one which is a robot that lives in a space and we just wanted to go from one configuration to another desired configuration. But from next week, inshallah, we're going to be looking at, we have a robot that is interacting with the environment. And we need to have this change of paradigm of trying to design a controller for this type of special systems. Today's lecture just looks different. Okay, so there's just some special stuff related to manipulators, but there's no new information in terms of all of the tools that you have. So we're going to be using exactly the same tools, writing stuff in state space form, computing the equilibrium points, calculating the stability with it using Lyapunov direct method, using Lassalle's principle, invariance principle, and then designing the controller in terms of a PD controller, in this way of having a potential function, taking the derivative and gradient and blah, 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 blah. So there is no tools, but just different applications. There are some stuff that are generic or very particular for fixed base manipulators. You're going to be seeing today that we're going to be exploiting the structure of this fixed base manipulator, so the dynamic equation, and this will simplify things a lot, okay? Compared to try to do it in coordinates or trying to write it down in terms of theta 1 and theta 2 and theta 3 and so on, you're going to be hopefully appreciating today this idea of doing model-based control and using the structure underlying this control under the system. So we're going to be looking at systems of this form, generic systems of this form. So you should be familiar now that any N-link manipulator, that's just a bunch of rigid bodies attached to a fixed base. So this is the condition. We have a fixed base, not a floating base. It's a fixed base, and all of them are connected to each other by, we're going to be focusing just for simplicity on revolute joints, 1 degree of freedom revolute joints. It could be extended to other joints, but again, just an extra, there are some extra complications, but we're going to be looking at the standard manipulator equations. So M of theta, theta double dot, plus C of theta, theta dot, multiplied by theta dot. We're going to be adding a friction term, okay, so to have this inherent damping in the system. And these are the gravity torques, and these are our control torques. You should know how to derive these equations from just the rigid body equations by now. If you did the assignment and looked at the tutorial of deriving these equations for a two-link manipulator, this should be familiar. If not, these are standard equations in robotics. Okay, so any robot can be written in this form. Again, provided the conditions I mentioned. The configuration space of this system is, if we assume for simplicity we have revolute joints, then we have all of the joint angles, so theta 1, theta 2, theta 3, up to theta n. And each one of these lives on a circle, so it takes values from minus pi to pi, one of them excluded. And in the end, when you take the Cartesian product of this space, you get what's known as the n torus. Okay? So the n torus, this is the shape of the configuration space. So the one torus is simply the circle. If you have one rigid body that's attached, it's just the pendulum. You just have it lives on a circle. If you have two rigid bodies, then they live on the torus. Remember the donut-shaped configuration space. And in general, you have this n torus. It's not comprehensible. It's something you cannot visualize, but abstractly, it's the same idea as the two torus and so on. We will cast this dynamic equation into the state space form. We're going to be choosing the states as the total angles. So theta here is the vector, or like the n tuple of theta 1 up to theta n. Theta dot is the n tuple of theta 1 dot up to theta n dot. And both of them together combined live in the tangent bundle of this configuration space Q. The state space equations, they look like this. They should be familiar to you. So x1 dot is equal to x2 because the rate of change of the first state, which is the angles, is the angular velocities. And the second one is given by this equation, which is nothing else than rewriting the top one. This is something that's standard and simplifies the analysis a lot, especially if we start to write a lot. That we're going to be taking this whole term, which is a function of theta and theta dot. Okay, and we're going to be calling it C of x. Okay, so all of the centripetal and centrifugal forces or torques are included in this term. The B of x2 is given by this term, which is nothing else than this should be a theta dot. So B of theta dot and multiplied by theta dot, we're going to be calling it small b of x2. So it's just all of these friction torques. This friction, I write it as a function of theta dot because it can be nonlinear. So we can have nonlinear friction and it won't change a thing. Just to show you the power of the tools that we're going to be using. It doesn't matter if we have just viscous friction or more complicated nonlinear friction types. And G of theta is just the gravity torques. This looks familiar to everyone, okay? Any questions? Everything will be built on this. If you have questions now and this anything that's not comfortable, you can ask now. Okay, so the first thing we want to do, okay, is just to show you something you already did in the assignment, try to show you for a generic n-link manipulator what are the equilibrium points of this system. This is something that you already played around with for the two-link manipulator, but I'm going to show you that this is a general result for n-link manipulators. So the equilibrium point, again, for the unactuated case, so we're not looking at any torque. So it's just, you start the manipulator and it keeps on falling by itself. In the case of the two-link manipulator, it's just a double pendulum falling with gravity. The equilibrium points are the states x1 theta, x1 star and x2 star. So x1 star are just the angles and x2 star are the angular velocities. They should satisfy x2 star is equal to 0. So the equilibrium points should have no angular velocities. They should be like stationary. And the x1 stars, they should satisfy g of x1 star equal to 0. Okay, so in the end, what we're looking for actually, no matter how complicated the equation is, we just take the gravity torques and see what are their zeros. What angles make this gravity torque equal to 0? And thus we found our equilibrium points. What is the proof of this proposition? I write it in terms of proposition to show you, just to get exposed to how we write the propositions and how we prove it. So the proof of this is the following. So we know that equilibrium points should satisfy x dot. So x dot is equal to 0, or f of x, which is on the right-hand side, is equal to 0. Just as a notation so that it's clear what, in terms of, to help you out in terms of the reading this. So 0 with n down, it means that it's the 0 in Euclidean space. So it's n zeros actually. It's the n tuple that's 0. So 0, 0, 0, 0, n times. And when I write here something like only 1 0, this means actually it's just 1 0. Okay, so if I write 0 is equal to this is a scalar. If I write 0 is equal to that, this is actually a vector of it all 0, just to make things easy. And I see here this is also this is a typo here, so this should be 0n. This should be 0n. Okay. So 0n is equal to x2, and 0n is equal to all of the equations in the momentum balance. Again, we remove the torques. So if you look here from the first equation, this implies that x2 should be equal to 0. Okay, we said that the velocity should be equal to 0. And if x2 is equal to 0, remember the term c of x, it actually had theta dot multiplied into it. So if theta dot is equal to 0, c of x is equal to 0. And b of x2 was also like a matrix multiplied by theta dot. So this term also goes to 0. So we're only left in the end with m inverse, which is a function of x1 multiplied by g of x1. So this vector, so remember, m is an n by n matrix, m inverse is a n by n matrix, and g is an n by 1 vector, okay, tuple. So these two multiplied by together will give you the 0n vector. Equivalently, and we're going to be doing this just to relate to something you already seen in this course, if we multiply from both sides by g transpose, okay, so in the end, I have a vector transposed multiply a matrix of the same dimension multiplied by a vector. So what do we get in the end? A scalar. Okay, that looks like this. Does this remind you of something? The quadratic form, exactly. The quadratic form, when we look at the matrix, and we look at the quadratic form of it, okay? So this is the term that we usually look at on the right-hand side. We want here that this quadratic term should be equal to a scalar 0. And there is something that's a property of this system. It's a mechanical system. And this M matrix is positive definite. It has to be always positive definite. No matter how complicated the robot is, it will always be positive definite matrix, which means that, and as an implication, the M inverse is also positive definite. Okay, so when you have a matrix and its inverse, the eigenvalues, the signs, they don't change. Okay, they have the same sign. So M inverse is also positive definite. And if you remember, when we said that we have a positive definite matrix and we multiply it and we put it in this quadratic form, we said that if the matrix in between is actually positive definite, then this term should be always greater than 0. And if it's always greater than 0, this means that it can only be 0 if this vector is equal to 0. So this, in the end, we have as a proof that this expression is equal to 0 if the g of x1 is equal to 0. And this concludes the proof. Okay? You can look at it at your own pace, but again, if you find any proposition or some lemma like this, then this is how we logically try to prove it. Okay? And maybe you've seen this in a paper before, but this is just as a practice, you can try to look at it at your own pace. Okay, is that clear? Yes. If the system was? Yep. Like this. Yeah. So this is what you had in the assignment. Okay. So you did this by yourself by hand, right? Okay. Is this better or what we're going to be seeing now? Okay. So this is how the gravity vector looked like in the assignment, right? In the two-link manipulator. Okay? If you solve the assignment. Okay. So this is the gravity vector. So the equilibrium points should satisfy the roots of this gravity vector. So we want to have that g of theta star should be equal to 0. We have the second equation, which is sine of theta 1 plus theta 2. This should be equal to 0 on its own. Remember, all of these gammas are constants, and they're positive. They don't change anything in terms of the roots. And if this term is 0, then this term should be 0. Sorry. And this term should be by itself 0. The only thing that satisfies these two equal to 0 are these four equilibrium points: 0, 0, 0 pi, pi 0, and pi pi. All of these physically mean down, 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 up, up, down, and up, up. All of these positions of the double pendulum, which was what we did in the assignment. In the interval. So the actual, just go back to the pendulum. The pendulum, the values of theta. So the actual pendulum as a configuration space lives on a circle, right? As if you look at the point mass, that if you just look at pendulum with the point mass at the end, and you just look at the configuration, I can describe it as something that lives on a circle, right? And this so x, y, and location that live on a circle, they should always satisfy a theta that lives from minus pi to pi. You agree? But one of them has not to be included because we identify actually that minus pi is equal to pi. So, and that's why, okay, we go to minus pi, and then, so this is an angle of 0, and then I'm rotating around this axis up to 180 degrees. You see? So this is the new orientation. But is this new orientation, is it pi or minus pi? You cannot have both. Otherwise, you're not going to have surjectivity. You cannot go back and forth. If you say that this is minus pi and this is pi at the same time, in your mathematical formation, you're going to have something wrong going back and forth between the angle and the position. That's why we have to exclude one of them. Because all of them are in terms of, okay, so again, so here, so this is theta 1, the first angle that goes from minus pi to pi. And the second angle goes from minus pi to pi. Okay. And minus pi, you see there's an open bracket, which means it's not included. And then we have the zeros included in both. So I have 0, 0, which in the middle, and I have here 0. And out of these, this whole, like this space, these are only the 4 equilibrium points that I have. You see, I'm not talking about the minus pi. If you look at it from in terms of, you remember what we did with the pendulum. If you look at this as not minus pi to pi with one of them excluded, but you look at them as r, you're going to get all of the multiples of this. You're going to get 0 and pi and 2 pi and 3 pi and 4 pi and minus pi and minus 2 pi and minus 3 pi and so on. You remember what we did with the phase portrait? All of these were just manifestations of the coordinate chart that we chose. But in terms of this physical space, or this physical configuration space, we got the correct physical equilibrium point. More questions? Okay, let's move on. So what we want to do now is to study the stability properties of only the origin. Okay, there's something that you can show, but I think you did it in the assignment, right? You actually showed that all of these three are actually unstable. You did that? Okay, good. And you showed that this one was undetermined. Okay, it was undetermined when you did the Lyapunov stability, when you did the indirect method, because we didn't have any friction. Okay, actually, if you add the friction from this example, you're going to find that it is asymptotically stable. Okay, so with the indirect method, you can show that it's asymptotically stable.
So any in-link manipulator, I can use getting the G of theta by 0 or the gravity vector, right?
Yes.
This is like a rule for only in-link manipulators.
I said here any link manipulator. This is the equation of any link manipulator, right? No matter how big it is, no matter how complicated it is, no matter if it has 100 degrees of freedom, exactly the same. Only, of course, absolutely. We're talking about here the unactivated case. Yes, absolutely. We're talking about the unactivated case. If you have an activated case, things get different. Okay, and also here we don't have any internal stiffness, so we don't have any compliance in the robot. If you have compliance, things also change. So this is really rigid bodies connected by revolute joints. The revolute joints, they have friction in between them. So, and that's it. So this is the ideal setting that we have. Okay. We want to look at the stability. We want to prove now, okay, something that you didn't do in the assignment. It was not asked, which is trying to prove that the origin is asymptotically stable using Lyapunov's direct method, not the indirect method using linearization, but the direct method. We're going to be using the total energy of the system, okay, as our Lyapunov candidate. So the total energy of the system is kinetic plus potential. The kinetic term is given by this. So you can either take it as is, or you can go back to the lecture. You remember when we discussed the M, and we said that you can derive it from the L, and there was the S, and there was the inertias in between. Okay, if you go back and go back to this expression and expand it, you're going to find that this half theta dot transpose M of theta dot with the expression that we discussed in terms of the definition of M is actually nothing else than the sum of the kinetic energy of all of the bodies. So the kinetic energy of the first body, the second body, the third body, up till the nth body. Okay, in the same way that you're all familiar with, which is half the twist transpose multiplied by the generalized inertia multiplied by the twist. Go back as an exercise and try to prove it for yourself. So this is the kinetic energy of the system, and this is the potential energy of the system. So the potential energy we're not going to be defining, so we're going to be writing it explicitly because it changes from robot to robot. But in all cases, the kinetic and the potential energy is a function that takes Q goes to R. Okay, and this is something different from the potential to the kinetic. The kinetic is always a function of theta and theta dot, but the potential is only a function of theta energy in general. The potential energy is only a function of the theta variable in general. So the potential energy eats a Q and so eats an element of Q and goes to R. It's a scalar function on this configuration space, and it's defined such that when you look at the gradient of it, okay, and this is the gradient in terms of the nabla, which is the vector version, not the covector version, which is the differential. This is the vector version of it. So it's the transpose of the other one, and it's equal to the gravity torques. Okay. This is very similar to when you say that I have, you remember when we had if you go back to a simple pendulum, as when you derive the equation, there's the torque due to gravity, right? On a simple pendulum. You all know how to derive it. It's minus mgl sine theta, right? And then if you write this torque as the gradient of some potential function, this potential function, you show it as mg multiplied by the height, okay, of the pendulum to the center of mass. You can actually derive, you can show this is always true. This is just as an example for today's lecture. Take it as something that's also as generic as these equations for an link manipulator. The potential energy of any link manipulator will always be such that when you take the gradient of it, you're going to get the gravity vector. When we introduced the gravity vector, we did it with Einstein's equivalence principle, or we looked at having a wrench on each rigid body, if you remember from the lecture, I think it was lecture 15. But we can also introduce it this way. Okay, if you do the Euler-Lagrange derivation, you can show that the gravity vectors are also given by this term. So this is just something I want to leave it abstract like this. If you have any example in mind, okay, you can try to prove it for yourself that this is always true. We're going to be using this total energy as our Lyapunov function. Okay? And we said this is something we can always do, but what is the problem is that we're going to be able to show in the end negative semi-definite. So remember the same drill what we've done so far. So this is our kinetic energy, okay? Just written now in terms of theta and theta dot, but x1 and x2. And this is the potential energy written in terms of x1 and not theta. This equation, it is a valid Lyapunov function because it's positive definite. How do we know that? The kinetic energy is quadratic. Okay, the term inside the m is positive definite. So this quadratic form is always greater than 0. So this is on the x2 side. Even though it's nonlinear, remember this is a function of x1, so it can be very complicated. But just because of the physics of the problem, this is always positive. Even the potential energy is always positive. Because when if this is energy, if this is potential energy, and you say, okay, I have something that has positive potential energy. We never say I have something that has negative potential energy. It has always positive energy, and it has a minimum when at our equilibrium point 0 and 0. So this is even as general that okay, even for any n-leg manipulator, we also have this to be a valid candidate Lyapunov function. So far so good. Okay. We will show now on the board, but this is just the end result. We're gonna go to the board and try to show this step by step. That the v dot, okay, which is the time derivative of this, again, the standard way the same way that we've seen so far, nothing new, will be equal to this expression. We're gonna be looking at it at the board now. We're gonna go to the board in a second. But you see, this is an expression which is negative semi-definite. Okay. So what can we do next? Lassalle's invariance principle. You're going to find that this is the v dot is equal to 0, means x2 is equal to 0. If x2 is equal to 0, you go back, you're going to, again, follow this line of thought until in the end you reach that we have one equilibrium point, which is the origin, and you can show that actually it's locally asymptotically stable. It's not globally asymptotically stable. Why? We have other equilibrium points, right? Just like anything that is a 0 of this vector is still a valid equilibrium point. How do we get rid of it? We look at the smaller state space, right? So we look at the Lyapunov function and we just exclude these equilibrium points and the same drill. Nothing new here. Okay. I'm going to skip, of course, all of these using Lassalle's principle. In many papers, you're going to find that there is no all of these like line of thought state. It's just stated in 2 lines using Lassalle's invariance principle. You can show that this is like that and done. Okay. It's something that's really recurrent, and you find it a lot of papers, and you do it again and again and again. Okay, of course you have to prove it for yourself on paper, but you don't need to write it in the paper or in the research article or in the end. Okay, but don't fly and say, okay, this is the true case, and just to get the paper published. Now let's go to the board. Yes.
On cases where we have this locally asymptotically stable,
yes,
almost global stable situation.
Yeah.
Is it safe to say that if we are in one of those states, or one of those equilibrium points, we can just add a little perturbation, and we are sure to eventually go to our desired state? This is
precisely what global asymptotically stable means. If you need to have something else. You need to show for this extension or for this better result, this strong result, you need to have actually that the other equilibrium points are unstable. Right? Because if one of them is actually locally asymptotically stable, then it's not only that you just start from a perturbation from it, you can also go to it. Okay? You have these in some complicated systems, and most of the systems we looked at, which is just these robotic systems, there wasn't anything like that. Maybe if you have a nonlinear stiffness, then you start to have this. Okay? So if you have a robot with some nonlinear stiffness and so on, you might have might have these 2 stable equilibrium points. Okay? And nonlinear dynamics is you can always make up some toy problems to show that in real life, and more on that. Okay. More questions before we go to the board? Okay. So this is what we want to do now. So we want to show the Lyapunov stability of the origin. Our Lyapunov function was this. We have the potential part, which is still abstract. We're not going to be saying what it looks like. It's just a scalar function, okay? That we know what it should satisfy. The V dot is equal to, again, it's a sum of two parts. So it's this one, okay, dot plus this one dot. This one dot, you see, it's a vector, matrix vector. So I use the chain rule of like the matrix multiplication. So which is half x2 transpose dot m of x1, x2. So I take the time differentiation of the first one and multiply the next two as they are. Then I leave the first one as it is and take the time derivative of the matrix. And the third one is the same. And then I leave the first two as they are. Multiply the time derivative of this term. And then I have here also the time derivative of that guy. The time derivative of this, okay, the scalar function in general, is given by the pairing, right, between the gradient of it with x1 dot. So I can write it as the gradient with respect to x1 transpose of E potential x1 multiplied by x1 dot. This term, again, just in case it's too complicated, we've wrote it in the past weeks in different forms. So we said that the time derivative of this guy, which is a function of x1, is equal to the pairing between d of E potential, which each x1 with x1 dot. Okay, you remember this part? Okay, and this is on the tangent space of this guy, and this pairing is given by this row vector multiplied by this column vector, or I can transpose this guy into the gradient, and then I'm going to multiply this one transpose multiplied by that one, which is this expression here.
Why did you write this delta this way, this x1 below and something like this?
Because if you have a function of more variables, okay, then you need to specify which one you're taking the differentiation with respect to. Exactly. Okay. You sometimes find there's no like subscript here. Sometimes you just write it like this, gradient. But there, I just want to be explicit on this part. You see these two expressions, this one. So this expression and this expression, they're actually the same thing, right? Because this is a scalar, and a scalar means one number, it's in R. And when I transpose that scalar, what do I get? I get the same thing. So if A, what's the transpose of small a? It's A. So this is a scalar, and this is the same scalar. If I transpose this guy, I'm going to get x2 transpose dot multiplied by the m transpose. What about the m transpose? It should be equal to m. Why? By definition, it's a symmetric function. Okay, by definition, sorry, it's a symmetric matrix. Okay, so this comes from the physics of the problem. So this is a symmetric matrix, and then I have here x2, okay, on the other side. So these two are exactly the same thing. So I have a half here and a half there. I can combine them into one. So I can write this as x2 transpose m of x1 multiplied by x2 dot plus and then this expression, what does this remind you? So this term, what does this remind you of? The gravity torque, exactly. So this is the gravity torque, okay, transposed, okay? So I have the G transpose x1 multiplied by x1 dot. Okay. So you see I have x2 dot here and x1 dot. How do I proceed? I substitute x1 dot and x2 dot with what? With the state space model, right? I go to the state space model. Here we're gonna look at the stability of the origin while with the torques equal to 0. So there is no actuation. Okay, so you can show that we're gonna get this expression. We can write it as make sense? Okay. So everything in here in this bracket is x2 dot, and x1 dot was equal to x2. And if I have a vector y transpose x2, I can write it as x2 transpose y. This is exactly what we did here. Okay. Sorry? The what?
And x1 and x2 dot is the equal.
Exactly. Oh, sorry. Yeah, absolutely. Thanks a lot, Tarek. So this expression is actually this one.
Yeah, and the m dot. The m dot.
This term is this one, and this one is that one. Sorry. Yeah. Sorry. Yeah. Thank you. Dot. Yes. Thank you.
The x means the x1, x2, right?
Yes, that's true. And I think we have here. Wait a second. We should have here. No. So this is the big one. Just to be C of x. And yes, this is short for x1 and x2. Okay. So this is the big X. So you remember this was we wrote that these two together are the small c, and these two together are the small b, and we just expand them because we're going to be using the structure that they have. So far, so good. Okay, easy. This one and that one, they get canceled out. You agree? Okay. And in the end, we're going to be left with this expression, minus b, sorry, x2 transpose b2, sorry, b of x2 plus half. I'm going to combine this m dot with this c together. So I'm going to write them as x2 transpose m dot of x1 minus 2c of x2. So far, so good? Anyone knows how to proceed? What? So how do we proceed? Yeah. So this is something only for robots. That m dot minus 2c, okay, is skew symmetric. It's a skew symmetric matrix. Okay, it's not for any robot, it's not for one robot, for a special type of robot, it's for all robots. Where does this come from? You remember the C comes from a lot of terms. It has the adjoint and blah, 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 blah. And the M comes again from inertias and so on. You can prove this for yourself, actually, using this expression. Take the time derivatives of there. You know that the time derivative of the big adjoint is related to the small adjoint. You're going to do a lot of juggling with a lot of equations, but in the end, you can show this. This has definitely to do with the geometric structure that we have on this manifold. Okay, so it's not just some trick. Okay, this is really into built in the geometric structure. So this is equal. So this is a skew symmetric matrix, which means that this term is equal to this whole term is equal to 0. By the way, this is sometimes a misconception. m dot is not equal to minus 2c. M dot is not equal to minus 2c, and so that we take all of this term equal to 0. It's that it's still a matrix, okay? But it's skew-symmetric, and this means that when I multiply it from the left and from the right by the same vector, okay, again making it into a scalar, into a quadratic form like this. So the quadratic form of any skew-symmetric matrix, this is the scalar that's equal to 0, not that this matrix is equal to 0. Okay? Just always keep that in mind. This is any skew-symmetric matrix. So Y transpose multiplied by B, let's not use the B, let's use A multiplied by Y. If A is equal to minus A transpose, this is equal to 0 for any dimensions. Okay, and even if A is a function of something, even if A is a function of Y non-linearly, okay, provided that there's some stuff on the I will not say more. Okay, so that's it. So this is, so all of this term is equal to 0. So in the end, we're left with this expression, and that was actually what we had in the proof. If you go back, so V dot was equal to only this term. It's negative semi-definite, and everything else falls. Okay, clear? Because what's inside is skew-symmetric. If you call this matrix m dot minus 2c something, call it matrix pi, capital Pi, then pi is a skew-symmetric matrix. That's a function of x1 and x2. Okay, clear? So that's it. So we're done here with the stability properties of the origin. Okay, so now we can show that, okay, it's asymptotically stable. Now let's start to do control. So our goal is, so now we want to do the PD control in the same way that we did it. So we want to do this idea of doing Lyapunov and trying to show, okay, that this, we want to go to the, not to the origin now. So if you turn on the robot, what it will do? It will just fall down, okay, to the ground, okay, to this origin, okay. So to this equilibrium point that we showed it's asymptotically stable. We want to have this robot not to fall down to the origin. We want to have it go to maybe to this location or to that location and so on, okay. So we want to have some desired configuration that we want this robot to go to, and then we're going to be using the control for that. So we want our objective is to stabilize the system. And by system, I mean the closed loop one, at this state, xd is equal to theta d with 0. What does that mean? We want to do stabilization control. We didn't talk about trajectory tracking, again, just because of time reasons, but again, tracking, you can always do it by looking at feed-forward stuff, okay? But this is only what we need for the feedback. So this is our objective. And what's the control technique we're going to be using? We want to look at this energy balancing control. Okay? The energy balancing control is the PD that we discussed, but when we derive the proportional part from potential function, and we derive the derivative term such that we have this damping injection. So our goal is to have energy balancing control, where the torques will be divided into two parts. One which is a proportional term that comes from the gradient of blah, 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 and the damping term comes from Lyapunov analysis. The error between theta and the actual theta and the desired theta will be simply given by their difference. Okay. Do we have a vector space structure on the n torus? So remember, we said that theta lives in Q, and Q in general is the n torus. Okay, so this is a T that's n. Okay. Does this have a vector space structure? It has a manifold structure. It's not a Lie group. Okay. Does it have a vector space structure? In general, not. We don't have a vector space structure. But do you remember this idea that we mentioned about the pendulum, that we actually, so the pendulum, so the simple pendulum lives on a cylinder where we have S1 multiplied by R. This is theta and this is theta dot. You remember this part? Okay. When we said that a pendulum has the configuration as S1, which is from minus pi to pi. Takes values on this circle. If I have a double link manipulator. I have S1 cross S1, which is T2, and so on. You remember actually when we drew the phase portrait. So what we did, and this is usually what we do, is that we take from minus pi to pi, and we draw it as if it's part of R, right? This is always what we do. We always plot from minus pi to pi as if some R. And whenever we reach the minus pi, what do? We just identify it with the theta, okay? This is usually the standard trick that we always do when we're doing this equation. So we always not usually use these numbers directly. We always wrap them such that this is from minus pi to pi. I'll give you an example. If I have, this is the actual place where the robot is, okay? So it's at it's an angle of 0. If I wanted to go to an angle of pi, I tell it go up, right? Then it goes to up. So now it's at an angle of pi. So it's an angle of 180 degrees. If I wanted to go to an angle of 1, okay, so you see it goes back, so on and so forth. But what if I have my actual angle is 0, and I give it the desired one to be equal to, I have the actual one to be 179 degrees, and the desired one is minus, let's see, I give it minus 181. It is out of the range, exactly. So but again, if you calculate 179 minus 181, and again, everything in radians, of course, what do you get? You get something very large, right? You cannot use this as the actual error between them. What do? You always take a modulus, okay, with the angle between 360, and you put it back in the end. So actually what we're interested in actually is just 2 degrees, right? It's not actually that we want to really have this huge number. We just want to have 2 degrees as an error. So this extra addition that you do, and usually do it in algorithms, right? There's actually a MATLAB function. You say it's I think it's called wrap to pi, something like that. What it does is that it will take all of these errors, differences, or these angles, and it will make sure it's between minus pi and pi. What we're actually doing there is that we're going to be treating the configuration space as Rn, but we're going to be identifying that whenever we have a minus pi, make sure it becomes pi, and so on and so forth. So we do it as an algorithm. But when we do calculations, we're going to be assuming that this is in Rn, okay? Provided the fact that you always make sure by an extra algorithm that's always between minus pi and pi. Is that clear? Okay. Yes.
Or also like the error?
The error in the end. Yeah, exactly. Of course, by the way, even if you make this, let me see. Let me give you an example. So let's say we said that we want the theta to be between minus pi and pi, right? This one included, which means that the values 180 in terms of degrees and minus 179 are included. Okay, you agree? So if I have here this to be 180, and I have the desired one to be minus 179, both are included, right? But the error bigger. Then I need to wrap it into this, okay, range, and so on. I do it by an algorithm. Doing it by this algorithm is nothing else than taking this, like this R2 or this Rn version of the state space and putting back into like a shape of a torus, okay, by algorithms.
So in terms of talking about, because you just mentioned now that the S1 is basically not a vector space.
Yes.
But then we're taking.
But it lives in R2. It's a part of R2. And if I take the difference, okay, but again, so here we're not looking at. So we say that this lives in S1, but we're actually looking at its angle version. Just to remind you. So whenever we say S1, we're talking about all of the points X and Y that live in R2, such that X squared plus Y squared is equal to 1. We're actually looking at the Cartesian coordinates, not the polar coordinates. But here we're talking about the angle, which is the A tan 2 of the X and Y and so on. Okay, So it's actually just a value from minus pi to pi. Okay?
But then, because what kind of bothering me is if we take it as an element of Rn, the subtraction or the error, wouldn't it violate some structure?
No, because we're going to be wrapping it. That's the whole idea. We're going to be always making sure we're going to be putting it back from minus pi to pi.
So that means the algorithm has to be
Wrapping. It has to do. It has to do this wrapping. So you calculate this difference and then you do the wrapping. You always add it as an extra step. Just in exactly the same way that with this example. But you just do it for n dimensions. For theta 1 and theta 1 desired, theta 2 and theta 2 desired, up to theta n and theta n desired. Clear? More questions? Which part? So here theta. So here, so the configuration space of theta. So theta here for an n-link manipulator will consist of theta 1 and theta 2 up to theta n. The simple pendulum is an example because it's a special case of this system for theta is equal to theta 1. We have only one joint. Okay? So in this one joint, where does it live? It lives from minus pi to pi. You agree? You agree? If you have two joints, where do they live? In this space, cross another version of it. If you have n links, you have this one multiplied by itself n times. You have the Cartesian product of this space. This one is not R, right? So it's only from minus pi to pi. It's an interval of R. It's an open interval of R. It's not R, but it's an open interval of R. When you cross it n times, you get this n torus, which is locally isomorphic to Rn, but not globally. So it locally looks like Rn, so it's a manifold, but not globally everywhere. Clear? Okay. Let me remove all of this stuff. So hopefully it doesn't. Okay, so let's remove all of that. Let's go back. This. So this is the error. And what do we want to do? Where is it? Yeah. So we're interested now because you see we're treating everything we're doing here as if it's Rn, right? And how do we do the potential function Rn? This should be familiar to you. So now we want to derive the proportional part as the gradient of the minus the gradient of some potential function. So the potential function we're going to be using, we're going to be calling it psi of theta is equal to half theta minus theta desired transpose with some matrix that we choose, some positive definite matrix Kp multiplied by theta minus theta desired. Rings the bell? Exactly what we did for the point mass. Okay, nothing else.
So we have already defined the Lyapunov analysis without this potential function.
Now we're going to be doing control. So what we did earlier was the open loop system without any torques. Now we have the torques and we want to design them. So what we're going to be doing next is use this as the Lyapunov function for the control. Yes, we're going to be doing that next. So now the proportional torque, or the one that that we want to have the minus of the gradient of this function, will be equal to, so this torque will be equal to the gradient with respect to theta of this psi of theta, which is equal to minus Kp theta minus theta desired. And this is in Rn. So far, so good. Exactly the same as what we did for the Rn. It won't be exactly the same. There will be a little problem now, and let's see what this problem is. If we take this now potential function, and we try to put it with our own total energy that we had and try to do Lyapunov analysis for the closed loop system. So this is now Lyapunov analysis for the closed loop system. What is our design? What's our closed loop Lyapunov? So VCL will be our closed loop Lyapunov. It's a function of x. we're going to be choosing it as the original Lyapunov, the one that we chose earlier, which was equal to the potential energy and the kinetic energy of the original manipulator without any control. And then we're going to have this virtual energy, the psi of x1 that we want to use it for the control part, for the proportional control. And again, if we expand this, we're going to find this is equal to half x2 transpose, just to remind you of mx1. We have the potential part plus psi of x1. Before jumping into seeing whether this is negative definite or its time derivative is negative definite and so on, you should never forget, before doing actually Lyapunov analysis, that this Lyapunov function is valid. How to check that? Has to be what? Positive definite. Not only that, it has to have a minimum at the desired point we want to reach, right? Because when we say v dot will be equal to negative, this means that the v will keep on decreasing up till it reaches one of the points that we're interested in. So we need to make sure that it's a minimum of this Lyapunov function. So let's try to do that. So the VC at x equal x desired. Remember what was x desired? So our x desired we want to reach is equal to theta desired and 0. Okay, so theta desired is theta 1 desired and theta 2 desired, and the 0 is, this is the 0 in 2 dimensions, right? So it's 0 for the theta 1 dot and 0 for the theta 2 dot. We want to stabilize the system. So if we plug in here for this term, x2 is equal to 0, what do we get? We get 0. What about the E potential at theta desired? And then we have psi at theta desired. Remember that the potential energy was a function only of x1, so we want to evaluate it as at theta desired. And this potential function that we added, the virtual one for the control, is also a function of x1, so we want to evaluate it as theta desired. So we get these two. This one, we chose it to be equal to, remember? We chose that this one, go back from the previous slide, is equal to this quadratic form. Okay. Does it have a minimum at theta equal to theta desired? Yes. Okay. So this is equal to 0. So in the end, we're left with this equation. Now the potential function, when we evaluate it at theta desired, can we guarantee it's always equal to 0? In general, not. But that's not the problem. This is actually not the problem. The problem, because if this is like a constant, we can always redefine the Lyapunov function by like removing this offset. Remember, I mentioned something like this before. So this is actually not the problem. The problem is that we need to make sure it's a minimum. You remember what's the condition for having a minimum of a function? The gradient should be equal to 0, right? So let's look at the gradient of VCL with respect to x, which is also a function of x. So it's the gradient of the first term with respect to x, plus the gradient of the psi with respect to x1, because it's only a function of x1. Now, this is an easy exercise for you to try out. You know how to calculate the gradient in a generic form, but also this is Rn, so this should be easy for you to do it with just your with your eyes. So this should be make sense? I have 3 terms, this one, and this one. This is a quadratic terms in terms of x2. So the gradient in terms of x should be this guy. I think there's something also missing. I think also we need a term here as the differentiation of this with respect to x1 multiplied by x2. Okay, but anyhow, it won't matter because when we evaluate this at x2 equal to 0, it will drop out. Okay, so there should be an extra term here. Okay, I'm just going to remove it for now. But in the end, what we're interested in is when we evaluate x equal to x desired, what do we get? This is the important part. This part will be equal to 0 because x2 should be equal to 0. This extra term, okay, which will have the partial differentiation of m with respect to x1 will also be equal to 0. This one, what does it equal to? It's equal to g, exactly. It's equal to the g at theta desired. and this term is equal to, if you go back to the psi of x1, when you take the gradient of it, we actually calculated it. It's only this part without the minus. It should be kp theta minus theta desired. When we evaluate it at theta equal theta desired, what do we get? We get 0. So this term should be equal 0. So this is the only thing we're left at. Is this equal to 0 in general? No. Why is that? We already proved earlier that only when the g of some angle is equal to 0 if this angle is an equilibrium point, right? These are actually the definition of the equilibrium point for this type of system. So what this equation is saying that if your desired angle is one of the equilibrium points, you can use this. Other than that, this is not a valid Lyapunov function. Okay. So the bottom line of this problem is that, so we need to compensate the gravity. What we did so far is trying to do proportional derivative control. But for generic robotic systems, this is not enough. You need to take this, the gravity will always be problematic. If you don't have gravity, you're good to go. The proportional term, you can continue and move on. No, you won't have a problem. Any idea of a robot that doesn't have an effect of gravity? Satellite, okay, space robot, okay, that's correct. What else? On Earth. It's gonna get wet. So. Exactly. A two-link manipulator that's not vertical but horizontal. It doesn't have any effect of gravity. You're not gonna have any G there. So this is an example. The SCARA has gravity because the end effector actually goes up and down. So if you exclude this one, if you only look at, for example, it's a three-link manipulator that's planar, then you get the fact that actually you don't have any G term. What we're going to be doing now is that, how do we compensate this gravity? We're going to be doing something very simple, but very powerful at the same time. We're going to be modifying the Lyapunov function. Yes, Mubarak. Sorry, could you repeat? So this is not a valid Lyapunov function because when you go to, so you remember when we said that we need the Lyapunov function to be like some sort of bowel around our desired point, which means that when I go to this desired point and I take the gradient of this function at it, it should be equal to 0. It should be a minimum, right? And it should be positive everywhere next to it. So this is a function that we don't know whether it's 0 at this point or not. But more than that, if you look at the minimum, it's not the theta desired, theta is equal to theta desired is not a minimum of it. Because when we took the gradient of this Lyapunov function, we found that we don't have 0. So it's not a minimum of it. What we need to play around with is that we need to modify this Lyapunov function such that theta is equal to theta desired, and so theta of the closed loop system is equal to theta desired, and theta dot of the closed loop system is equal to 0. We need this to be a minimum of this, okay, of this function. Any ideas of the easiest way to do that? I'm gonna come to that. No, it's yes and no. So I'm not gonna say yes to that. No. Feed forward. Try to see in terms of Lyapunov analysis. How can we do it by modifying this Lyapunov function? Yes, exactly. We're gonna be modifying psi. So let's see. But actually I need to copy everything here, otherwise it will be too much to write this again. Okay, but okay, let's just do it. This is our psi function. Let's see, can I copy? No. What? There's no duplication for the whole page, unfortunately. Let's see. There's a delete here, so I don't want to play around with it. So, okay, so again, I'll try to do it very quick. You see this psi? Okay, I'm gonna modify it with an extra term. Okay, so now consider this modified Lyapunov function. Now consider this modified psi, which I'm gonna have it look like this. minus E potential of theta. Okay? What is now the proportional term? The proportional term is equal to minus the gradient of this guy, which is equal to minus Kp theta minus theta desired. What about this guy? It should be equal to plus the g of theta. Exactly. And then I'm going to be compensating the gravity in this way, because when I take this new psi and I add it to the old v, and I look at the closed loop Lyapunov function, now look at the Lyapunov function, what does it look like? So the VCL, which is equal to v of x plus psi of x1, this term had kinetic energy and potential energy. This term has something related to this gain, this quadratic function in the error in the theta, but it also has minus of the potential energy. What happens to these two? They cancel out. So in the end, you're left with something that looks like this. This is half x2 transpose m of x1, x2, plus half x1 minus theta desired transpose kp x1 minus theta desired. Here, instead of theta, I write it in terms of theta desired, x1, okay? Now it's trivial to see that actually I do have VCL at x desired, which is VCL at theta equal to theta desired and 0. What do I get? Is equal to 0. And it's clear that for any other point, VCL is actually greater than 0. So it is positive definite. Is it local or global? Global. It's global. Do we have any? So let's go now to the Lyapunov analysis. So move on with the Lyapunov analysis. Do nothing else than exactly what we did. Okay. Everything that we had earlier will just keep canceling out in the same way. You're gonna get. You can show very easily that VCL dot is equal to minus x2 transpose b of x2 plus x2 transpose multiplied by the damping term. Everything else was cancelled. Okay, we designed it this way. We designed that the proportional term would cancel, would be actually precisely related to the gradient of this function. So whenever we do the stuff with the v dot and so on, everything will cancel out. Okay, try it at your own pace. And this is the final result that we get. So any ideas of how to choose the tau d? What is the easiest thing to choose in the tau d? Easier than that. 0. I already have friction in the system. So it will actually stabilize itself by the internal friction. But what's the problem of relying on the internal friction of the system? It's uncontrolled. I cannot make sure how fast the system stabilizes or how slow it is. Maybe it stabilizes faster than what I want or slower than what I want. Okay. Remember when we played around with the pendulum? Okay, if we play around with the actual friction of the system, it might keep on oscillating forever up till it reaches after 10, 20, 30 seconds. But what we want to do is with control, we want to enforce this to be faster or slower based on what we want. So tau d, so the easiest thing for this thing is that tau d is equal to minus kd multiplied by x2, where kd here is any positive definite gain function that you choose. In the end, you can conclude that the VCL dot is equal to minus x2 transpose b of x2 plus kd multiplied by x2, and everything here is positive definite. Then we actually show that, what is the conclusion result that we have? That x equal xd is globally asymptotically stable, not almost. It is actually globally asymptotically stable. Starting from any initial condition, I can reach this part. What about this equilibrium points that we had, the other three? Why didn't we see them here?
By the time you do theta minus that, you don't have the
Because we already compensated for the gravity, you see? It was the gravity term, where is it? Yeah, this one. Yeah, this term. When we compensated for the gravity, The closed loop system doesn't have these equilibrium points. It actually has only one of them, which is theta is equal to theta desired and theta dot is equal to 0. This is the only equilibrium point that we have. So even if this is negative semi-definite, move on with Lyapunov, with Lassalle's invariance principle, and you can conclude that we have a globally asymptotically stable equilibrium point. Okay? Yes.
Previous slide, why didn't we include in gamma x1? Yeah.
Where?
Why didn't we, yeah, BCL.
This
Why-
one here.
Yeah. Why didn't we put minus
This one.
potential of x1?
We added it, but it got cancelled with that term. This is the original potential energy in the V. And I modified the psi to have minus of this one. They cancel out from the beginning. I don't need to do anything else. Okay? And inside, yeah, that's it. Okay? Any more questions? Easy? This had, because we actually had a manifold structure, and because of this manifold structure, again, it was not as trivial as this one. So this is almost Rn, right? So just plus or this fact of only with this warping of angles. You cannot do that because then you don't actually have say, let's see. This is exactly the same. So it's exactly the same. But here, from what we have here is that we're going to be getting this extra term, you see? You're not going to be having this extra term. So this extra term comes from the gradient of this. So you need to actually have it already there. Okay. Yeah, I think that's it. 1 second. Okay, I think that's okay for now. We're done, but I need just 3 minutes because no. Save. Or okay, maybe I'll comment on it next time. Okay, but we're almost done. Okay, so there's just one last comment on the relation between this and feedback linearization. Who's familiar with feedback linearization? Okay, so the majority don't know it, so let's keep it for next time. It's just a small remark. That's exactly what we did. Because the controller, adds energy to the system, right? So now when we say I want the robot to go from this configuration to this configuration, okay, I'm just treating this as the controller to be part of the system, looking at the closed loop system, and I'm looking at this new desired state as an equilibrium point for the closed loop system, and the system will just stabilize to it. This is the whole idea of doing Lyapunov based control. We're thinking of the control part as that we're actually stabilizing the closed loop system to this equilibrium point. Just exactly in the same way that the original system would stabilize to the origin, this is exactly what we do in this case. Okay? Yes, exactly. That's exactly what we're going to be doing. So if you choose no extra damping, you're going to be just using the original damping of the system. If you want to have faster or slower, then you need to add or reduce the damping of this system by this control. Okay? Thank you very much. جزاكم الله خير.